In this video, I'll be talking about a few simple calculations for the canonical and ensemble pertaining to the ideal gas. In the previous lecture, we talked about the canonical ensembles and arrived at this particular equation for the partition function. Right, and in the previous lecture I described that this particular part is that for the ideal gas. So let's take this further and see whether we can derive some simple thermodynamic properties for the ideal gas system. Where so this is the ideal part of the partition function where lambda is given by h by so let's first start with the free energy. The free energy is given by the negative log of the partition function. So let's first take the log of the partition function. So we can expand this as n ln n minus n. So let's do that. Okay, now that we have the expansion of the log of the partition function, let's go ahead and derive the free energy. So this is the equation for the free energy of the ideal gas. So now let's say if we can derive the ideal gas law, that is PV equals to RT. So the pressure is given by this is the equation for the pressure in the canonical ensemble. We already have derived this log of the partition function, so we can directly substitute it. So let's do that. So since all these terms are not dependent on the volume, they'll be directly 0, and we have dou n dou ln V by dou V. So this should be, this whole thing is 1 by V. So we have n by V. So let's substitute it back. We have to kBT times this value, that is n by V. So we have PV equals to n kBT. So if we have n is equal to the Avogadro number, that is, then we have PV equals to RT, where R is equal to n into kV. Okay, now let's check out the specific heat. At constant volume. So we know that the CV is actually defined by dou E by dou T at constant volume. This is the definition of the specific heat. Now let's see what the energy looks like in a canonical ensemble. E is given by kBT square dou ln Q by dou T. Okay, let's plug these values. Right, so if we were to do the derivative with respect to temperature, this term would be 0, this term would go to 0, and this term would go to 0. All that we would have is this term. So let's do that. Remember that lambda equals to H by so lambda is actually a function of temperature, so therefore we can actually take this derivative. So let's say what happens. This is just simple math. Minus 3n T square. So this term is not dependent on the temperature. This is Planck's constant, so this goes to 0. So we have minus dou by dou T of ln 2 pi m kBt. So this half, so we know this rule of exponents for the log function. So the half comes here. So we have this minus into minus is plus 3n kBt square by 2, and this becomes dou by dou T of ln 2 pi m kb plus ln T. So this term goes to 0 as this is not a function of temperature. So we have 3n kBt square by 2 into dou by T of ln T. The total energy E is 3n kb T square by 2. So this term is actually 1 by T to 1 by T. T gets cancelled, so this becomes 3 by 2 n kBt. So if we combine them together, this becomes the gas constant R. So E is basically 3 by 2 RT. Now we saw that Cv is dou E by dou T at constant volume. So this becomes dou by dou T of 3 by 2 RT, and this gives us 3 by 2 R. So the specific heat for the ideal gas is given by ideal monoatomic gas is given by this. Okay, thank you for staying. Please subscribe to this channel for further videos. Thanks.